Hi, this is Dr. Graves with Cal State Northridge, and we're back with a discussion of Chapter 3, The Earth's Atmosphere, or Geography 101. And this chapter is important. It's reasonably short, but it's important for you to understand it, because if you don't, then it becomes really difficult for you to understand much at all about the weather and weather processes. The learning objectives drawn out here, we probably, because it's online, we won't have you do this, but this will be you may be asked to list the components of the modern atmosphere and understand the relative percentages of what's in the atmosphere, describe the conditions in the stratosphere, particularly what we're looking for is the function of the ozonosphere or the ozone layer, and then there'll be a bit about natural and man-made or anthropogenic pollutants in the lower atmosphere. And then you won't really have to do this, but have to be able to understand a diagram illustrating pollution and how it works, and then where smog and pollution comes from. So the atmosphere as we know it, the air in surrounding the world, has gone through a series of changes over the millennia, and this is the modern atmosphere and what it is composed of, and really that's what you need to know something about. And we will come back to this time and time again. When we talk about atmosphere, it's really just air. And air, a lot of people think that what we breathe is simply oxygen, but the air that we breathe is only about 20% oxygen, and about percent of air is this N2, which is nitrogen. And we think of nitrogen as being something in the soil, but it's very plentiful in the air, and some plants are able to convert what's in the air to nitrogen that's in the soil. About the rest of air is made up of a whole bunch of other small bits and pieces of gases, but they are exceptionally important, as we shall see. There are variable gases, meaning that there are some that are in the air at much greater concentrations sometimes, water vapor being among those. It's essentially steam or fog, as you might want to think it. And that goes from 0 to 4%. And then carbon dioxide, CO2, is small. Unfortunately, that is, despite how small it is definitely increasing, and increasing rapidly in a way that is bad for the health of the planet, and more importantly, the health of human beings and the animals. Air is odorless, colorless, tasteless, and formless for the most part. But it doesn't mean that it's not there. And so we want to think about the air being thick. The thickness of the air, or our atmosphere, 480 kilometers, it rises into space. And then beyond that, sort of what we call the exosphere, and that's the out of space. And there's really not much air of any sort up there at all. Air does have density. A lot of little kids think that air weighs nothing, but it does. And the easiest way to experiment with that is to weigh something like a basketball when it's deflated, and then pump it up with air, and then weigh it again on a scale, and you will see that it does have some mass. The more that you pump into a basketball is volume, the more mass, and that means more density. And so the air molecules are much more crammed into the basketball when you pump it up. Um, on average, air has a density at sea level of about 1.2 kilograms per meter square. Our bodies don't feel that. Um, you can feel that water is far more dense, and sometimes if you dive to the bottom of the pool, where that density is greater. You can feel that particularly on your ears. You can feel changes in the density of air on your ears as well as you get in an airplane or even sometimes a car and change altitude. At higher altitudes, there is lower air pressure because there is lower density of the air molecules. They're not as close to each other. They're spread further apart. And again, most of the time we can't sense that. Our ears sometimes notice it because they pop, so to speak, when you move higher or lower through altitude. Closer to the Earth, the air molecules are much closer together. They are drawn down like everything else by gravity, and they're sort of smashed together. As so, what you need to keep in mind as you go up in elevation, further into the higher reaches of the atmosphere, the air pressure is lower and lower. And here's one of the things you absolutely should remember is that we measure air pressure in terms of millibars, and it is 1013.2 millibars on average at sea level. But as you go up through the atmosphere, higher and higher, that this air pressure drops lower and lower. You'll need to keep a lot of this in mind as we move on towards weather. So you may have gone to the mountains at some point and brought with you food or snacks from here in Los Angeles. Here's one of those instances in which you can notice the change in air pressure. This container of Special K cereal, you'll notice is the lid on it is raised upwardly because the air pressure out here in the mountains is lower than it is inside the container of Special K. And so when this Special K was packed, perhaps at sea level somewhere or near sea level, there was an equal number of air molecules on the outside of the container as on the inside of the container, and so the lid would have been flat. As you go further up through the atmosphere or at a higher elevation, the air molecules in here have less force upon them, keeping the lid flat than they did at sea level, and so therefore this lid rises up. I took another picture of this up in Yosemite. Here all of the bags of Lay's potato chips, which presumably were packaged at a lower altitude, brought north, and so all of the air is puffing these bags of chip outward because not because somebody has put more air into the bags, but because there is less air on the outside of the bags pushing them in. So these are good little lessons on how all of this works, and if you can internalize this, it'll be a lot easier for you to understand how weather processes are working later in the semester. So we'll turn our attention from the pressure profile to what is in the atmosphere now. So at very high altitudes, over 80 kilometers and up, there is a layer of the atmosphere called the heterosphere. Hetero means distinct or different, and at the top of the heterosphere there's almost nothing of what we would know as air, but it is a kind of air made up of hydrogen and helium. Those are the two lightest elements, and they are least affected by gravity, so to speak, or they're shoved up there by the denser atoms lower, and so they're way up high. The lower heterosphere has more nitrogen and oxygen in it, just as it does in the homosphere. But the real difference is that in the homosphere, virtually everything is all mixed up. It's uniformly mixed, and that's the homo part, meaning it's all one, as in homogenized milk. Homogenized milk is the kind of milk where the whey, the water, and the milk fat and everything is all mixed together, and its top of the jar of milk is the same as the bottom. The only exception in the homosphere is the ozone layer, which is a special layer of the atmosphere that exists from about 20 kilometers to about 50 kilometers up, and it is made up of a great percentage of ozone, or 3 oxygen molecules together. And this is really quite important because of the function of ozone as an important protector of the Earth's surface from harmful UV radiation. So here's a chart or a graphic from your book. The most important thing to know is that about 80% is nitrogen, 21% is oxygen. There's a little bit of argon and neon and helium in the atmosphere, but almost none of anything else except for this carbon dioxide, and we'll keep an eye on that. And the last of these 3 sections is the temperature profile of the atmosphere. There are 4 zones where the temperature behaves differently in the atmosphere. Now, of course, the most important one is the troposphere. This is where we live, down here below about 50,000 feet. And in the troposphere, you're going to notice that the temperature gets lower, about 6.4 degrees Celsius per kilometer, and this is called either the normal lapse rate or the environmental temperature lapse rate. So as you go up higher in elevation, the temperature, the air temperature, decreases about 3.5 degrees Fahrenheit per 1,000 feet, and that's why it's really cold at higher temperature. So those old World War II aircraft that were flying up here and were not pressurized, those fellows had to wear exceptionally thick winter clothing because it gets so very cold, sometimes minus 20 degrees Fahrenheit. In the stratosphere, which is 18 to 50 kilometers up, the lapse rate changes, and it actually gets warmer with altitude because that area is absorbing ultraviolet radiation in the ozone layer, and the absorption of all that radiation creates higher temperatures. The mesosphere is a really high, from about 50 to 80 kilometers up, really quite cold. Temperature decreases with altitude again, and sometimes we can see these noctilucent clouds, which are really pretty amazing. Here I'll show you a picture of one, and these are visible at night because they are so high above the surface of the Earth that they are reflecting the sunlight that is far below the horizon. And the last little bit here is the thermosphere, which is at 80 kilometers and above, and once again the temperature rises to quite hot. There's a lot of direct contact with solar radiation out there, and it doesn't, you have to keep in mind that you wouldn't necessarily feel hot because the density of molecules is so low, so spread out, that you would not have anything that's actually hot touching your skin, or a thermometer for that matter, and so you would be unable to feel it in terms of sensible heat. And at that note, I'm going to pause and stop the video and get it recorded, and that's the end of part 1.